Hi, my name is Harry Hu, and this is my Lab 2 Motion of a Falling Object lab report. For the lab instructions, we were asked to observe the motion of an object dropped from rest that fell directly down. We first captured a video of the motion, then analyzed the video in Tracker. We then constructed two computational models, one that accounted for gravity and no drag, and one with gravity and drag. Then we were asked to compare the two different computational models and observe. Here are some basic and introduction concepts. For the first three laws, these are Newton's three laws. Some important things to keep in mind are that unbalanced forces cause acceleration, and our acceleration is due to gravity, which is constant. And the only forces acting on the ball are the gravity and drag, but only in the y component direction. Here are some of our formulas and equations. Most of these equations we have done or reviewed before, but some new ones would include gravity force, which is negative mg, where g is 9.8, and drag force, with a negative b constant. Here's our tracker experiment. We were dropping the ball from rest to the bottom. Here's our Glowscript program. So in our first computational model that we're going to create using our Glowscript code, we're going to show the motion with only the effect of gravity, which means that we're going to neglect the drag force. So in our code, we're going to change the mass to 0.0027. We're also going to set our initial position of velocity to the points from Tracker. And here it is. We also changed the net force by adding on to the force of gravity by multiplying mass times that 0.8. In our second computational model, we're going to do the same thing, except we're not going to neglect the drag force. So that means we're going to add in a proportionality constant, which I solved for, and we're going to set the time to 0.567. And here's our second computational model. So we can see that in our computational models, the one that included the drag force with the gravity is closer to the actual observed motion. And this makes sense because in real life, we also have to account for the drag force, which is created by the air coming down. However, the lines are not exactly the same between the observed motion graph and computational model graph because it was impossible to correctly predict this 100%. And what does it mean in terms of terminal velocity? Terminal velocity occurs when the force of drag has exactly balanced with the force of gravity. However, none of these models predict an exact terminal velocity because it is impossibly 100% accurate. But the closest one would be the observed graph. So what if one of the objects was thrown downward? We would say that the terminal velocity is the same because it starts from the same height and the same object. However, the one that was thrown downward will reach terminal velocity quicker because its initial velocity was different. To summarize, they will both have the same terminal velocity, but will just reach the floor at different times. Thank you, and have a good rest of your day.